Hello friends, good afternoon and welcome to EduSet live lectures. Dear friends, in the subject of physics, today we will be talking about interference of light part 2. To discuss this topic, we have with us our subject expert Dr. Sonia Bansal. Dr. Bansal is assistant professor in YMCA University of Technology, Faridabad. Without further ado, we would like to welcome ma'am to the studios and request her to start the lecture. Welcome ma'am.
Thank you. Friends, last time we discussed about the optics and we discussed about the interference of light. In the interference of light, we find the interference of light can be obtained by the two methods, by the division of wavefronts, where we discuss about the Young's double slit experiment and the Fresnel biprism. Then the second part is the interference of light by division of amplitude, where in this lecture we discuss about these two experiment. First is Newton's ring experiment and second is the Michelson interferometer experiment to get the interference by division of the amplitudes. Basically, these techniques used to produce the interference. Before start, just I remind some points about the interference. There are the techniques for producing interference. The phase relation between the waves emitted by the two independent light sources rapidly changes with time and therefore they can never be coherent, though the sources are identical in all respect. But for the interference, we require the two coherent sources. The two sources are derived from the single source by some devices. Means we have the single source and we divided it into two parts by using the two slits. Then any phase change occurring in one source is simultaneously accompanied by the same phase change in the other source. Therefore, the phase difference between the waves emerging from the two sources remain constant and the sources are coherent. Means coherent is the basic condition to get the interference. And I already discussed about that. The techniques used for creating the coherent sources of light are wavefront splitting and amplitude splitting. In the wavefront splitting, wave dividing a light wavefront emerging from the narrow slit by passing it through the two slits closely spaced side by side. These two parts of the same wavefront travel through the different paths and then reunite on the screen to produce a fringe pattern. This is known as the interference due to wavefront. The method is useful only for the narrow sources and examples are Young's double slit experiment, Fresnel double mirrors, Fresnel biprism and Leuer's mirrors that we already discussed. The second part is the amplitude splitting. In the amplitude splitting, the amplitude means intensity of the light wave is divided into two parts, namely reflected and transmitted component by the partial reflection at a surface. These two parts travel through the different parts and reunite to produce the interference fringes. This is known as interference due to division of amplitude. Optical elements such as beam splitter, mirrors are used for achieving amplitude division. Moreover, the source should be broader in this case as compared to the wavefront splitting. Examples of this type of splittings are Newton's ring experiment and Michelson interferometer. Newton's ring experiment and Michelson interferometer come under the division of amplitude. Before starting the Newton's experiment, first we discuss about the interference of light by the thin films, means we discuss about the cosine law. Here we are having a thin film of the thickness T and here this film is in the medium 1, medium 2 and medium 3. By using this we can calculate the path difference. Here the two rays will destroy each other if the path difference between them is odd number multiple. Means we are calculating the condition for the minima and condition for the maxima for the interference of light by the thin film, and we can get the 2 mu t cos theta is equal to n lambda, which is a condition for the minima for the transmitted light, and this condition when this condition is satisfied, the film will appear dark in the reflected light, and this is a condition for maxima. 2 mu t cos theta is equal to 2n plus 1 lambda by 2. Part difference of the transmitted light will be calculated by P, which is equal to 2 mu t cos theta. In this case, there is no phase difference due to reflection at B or C. Here at B and C, there is no phase difference, because in either cases light is travelling from the denser to rare medium. Hence, the effective part difference between B T1 and D T2 will be 2 mu t cos theta, and this medium is air. Condition for maxima and minima in the transmitted light. The rays BT1 and DT2 will reinforce each other if 2 mu t cos theta is equal to n lambda, where n is equal to 0, 1, 2, which is the condition of the maxima. The film will then appear bright in the transmitted light. This is a condition for the minima. The two rays will destroy each other if effective part difference between BT1 and DT2 will be 2 mu t cos theta is equal to 2n plus 1 lambda by 2, where n is integral 0, 1 and 2 and so on. This is a condition of the minima. In this case, the thin film will appear dark in the transmitted light. Maxima and minima in the reflected and transmitted light. In both the conditions for maxima and minima in the reflected light are just the reserve those of in the transmitted light. In one it is appears dark, in another it is appears bright. Hence the film will appear bright in reflected light, will appear dark in the transmitted light, and vice versa. Now, we calculate the fringes of equal thickness by using the Newton's ring experiment, which is due to division of the amplitude. Here in the diagram, we see this is the setup of the Newton's ring. This is the source, here from the source, and the light coming from the source pass from the focusing lens, which is represented by the C. C is the focusing lens, and from here light will fall upon a glass plate G1, which is inclined at 45-degree angle. From C, light will fall upon a glass plate, and from here it is reflected and refracted, and it is reflected and moved towards a setup. What is a setup? This is a glass plate on which a plano-convex lens is mounted. A plano-convex lens is mounted on a glass plate, and light from the glass plate G1 fall upon a lens L and the glass plate G. From here it is reflected back and moves towards the microscope, and here we can get the pattern. Pattern means interference pattern we will get, and the concentric circles we will get in the Newton's ring experiment. Now, formation of the Newton's ring. How we get the Newton's ring? Here, this is the flat glass plate and this is the plano-convex lens. Light from the source fall upon a plano-convex lens and then glass plate. The light will reflect from the lower part of the plano-convex lens. From here, this you see the ray A1 fall upon a lower part of the plano-convex lens and light is reflected from here, and the second light, because we require the two rays. So, one we will get from the lower part of the plano-convex lens, and second part we will get the upper part of the glass plates, and these two coherent light used to get the interference pattern. And the when a plano-convex lens of a large radius of curvature is placed with its convex surface in contact with a plain glass plate, an air film is formed between the lower surface of the plano-convex lens and the upper surface of the glass plate. As we see in the diagram that here air film is enclosed between the, and the thickness of this air film is gradually increases from the point of contact. This is the point of contact, and here you can see the thin film gap is the gap between the plano-convex lens and the glass plate is gradually increases, so that the air film between that is also increases gradually. The second part is the thickness of the film gradually increases from the point of contact outwards. If the monochromatic light is allowed to fall normally on this film, as I already discussed about here, a system of alternate bright and dark concentric rings with their central dark is formed in the air film. In this diagram we see that this is the central dark and this is the dark ring, this is bright, dark, bright and dark. This pattern, interference pattern, we will get through the Newton's ring experiment. This is called the Newton's, these rings are called the Newton's ring. Now previously we proved Newton's rings are formed as a result of interference between the light waves reflected from the upper and lower surface of the air film. The effective part difference between the two rays is P is equal to 2 mu t cos theta plus lambda by 2. What is mu? Mu is the refractive index of the film. Here we are considering the air, so its value will be 1. What is T? T is the thickness of the film at the point D, and theta is the inclination of the ray. This factor lambda by 2 is introduced here. The factor lambda by 2 accounts for the phase change of pi on the reflection at the lower surface of the film. In this manner, we get for air film mu is equal to 1 and the normal incidence of the light theta is equal to 0 degree. Here if you see that here this light is falling normal, and here the value of theta is 0, and in this case we have the some value for the theta. But if it is fall normally, then theta will be 0. So this point P will be 2t, as mu is equal to 0, then this term and theta is equal to 0, then we are remaining 2t plus lambda by 2. Now the effective part difference between two rays for air film mu is equal to 1 and normal incidence of the theta is equal to 0 degree is P is equal to 2t plus lambda by 2. Now we calculate the condition for the maximum intensity, means for the bright fringes, and for the dark fringes, means minimum intensity. For the maximum intensity, we know that P is equal to n lambda, where n is equal to 0, 1, 2. Here we put the value of P, which is equal to 2p plus lambda by 2 is equal to n lambda. Here we calculate the 2t is equal to 2n minus 1 lambda by 2. This is condition for the maximum intensity. The condition for the minimum intensity means dark fringes, P is equal to 2n plus 1 lambda by 2. We put the value of P here again, 2t plus lambda by 2 is equal to 2n plus 1 lambda by 2. Now 2t is equal to n lambda. The condition to calculate the value of, here we are having the t, we calculate the thickness T by using this diagram. This is the diameter of the bright ring. Here we consider a glass plate on which plano-convex lens is mounted. If we take the full circle of that, let LOL dash be the lens placed on the glass plate AB, the point of contact is O. Let R be the radius of curvature of the curved surface of the lens. Here we consider the radius of curvature. Now in the diagram we will see that this point is A, B, and this is L, L dash, which represent the plano-convex lens, and the point of contact is O. Now if we take the radius, radius is the R. The thickness of the film is denoted by PO dash, which is equal to T, and this is the radius of curvature R. Center C is the center point. Now the remaining part is EN will be 2r minus t, 2r minus t, and then what is the OO dash is represent the length of the film. Now rho n is the radius of Newton's ring corresponding to the point P where the thickness of the film is T. Now draw the perpendicular Pn. This Pn, we will draw the perpendicular on the EO, and we will get, according the property of the circle, we get Pn square is equal to On cross Ne. This is On cross Ne. Now what is Pn, which is Pn square, which is equal to rho n square, and On, this is On, this length and this length are equal, so we can put T here. Then we can put T is equal to Pt is equal to On. So we can take here On is equal to T. So we put T here, and Ne. What is Ne? Ne from here we already calculate that, which is equal to 2r minus t. In this manner we can get rho n square is equal to 2rt minus t square. Since t is very small as compared to the radius, so we can neglect t square from here. Then final equation we have rho n square is equal to t into 2r minus t, and we can replace this t square and we have only the 2rt. We have this part only, t square will be neglected. Now here 2t is equal to rho n square by 2. Now condition for the bright fringes we already solve it, which is 2t is equal to 2n minus 1 lambda by 2. Put the value of 2t here, which is rho n square by r is equal to 2n minus 1 lambda by 2, and rho n square is equal to, we take r that side, then it will be rho n square is equal to 2n minus 1 lambda r by 2. Now for the bright fringe, dn be the diameter of the nth bright ring, then dn is equal to 2 rho n. Then dn square is equal to 2n minus 1 lambda r. Now dn is equal to, we take the root of that, and then dn diameter, which is directly proportional to the integral of 2n minus 1 is an odd number, where n is the integral and 2n minus 1 is an odd number. We can say that the diameter of the bright rings are proportional to the square root of the odd natural number, as its value is 2n minus 1. The diameter of the first few rings are in the ratio 1 ratio root 3 ratio 5 root 5 in the ratio of root 7, and these values are 1 ratio 1.7 ratio 2.2 ratio 2.4. The separation between successive rings are in the ratio 0.7, 0.5 and 0.4. The separation decreases as the order increases, as we see also in the diagram. This is as the separation increases and we can get the orders increases. Now diameter for the dark ring. The condition for the dark ring, 2t is equal to n lambda. Again put the value of t, already solved, rho n square by r is equal to n lambda. If dn be the diameter of the nth bright ring, then rho n is equal to dn by 2, and here we can get dn square divided by 4r is equal to n lambda. We calculate the diameter, so we take dn is equal to 4n r lambda 1 by 2, and dn is equal to 4n r lambda 1 by 2 n 1 by 2. It means diameter directly proportional to root of n. Diameter of the dark fringes are proportional to the square root of natural numbers. What are the applications of getting the interference by using the Newton's ring experiment? by using this we can check the thickness of the surface and we can check the surface is uniform or not. These are the applications of the interference. The next experiment is division. Next experiment for the division of amplitude is Michelson interferometer. What are the importance of this experiment? This experiment was done in 1887 by the Michelson-Morley experiment. Michelson along with the Edward Morley used this interferometer in the famous experiment, Michelson-Morley experiment, in the failed attempt to demonstration of the effect of hypothetical ether wind on the speed of light. This experiment left theories of light based on the existence of the ether without experimental support and served ultimately as an inspiration of special theory of relativity. In this experiment, here we are having a source. Again, we have to fulfill the condition of the interference. So, we require the two coherent sources. From the single source, we generate the two virtual sources. What is the arrangement of this setup? Now, we see the arrangement of Michelson interferometer. This is the source. We have the two mirrors, mirror M1 and mirror M2. Mirror M1 is the fixed mirror and we can move the mirror M2. These mirrors M1 and M2 are perpendicular to each other. Here is a glass plate P1 and this point is O. Glass P1 is partially reflected, so we can get partially reflected so that we can get the reflected and transmitted light from here. Now the light from the source passes from this glass plate and moves towards the and reflected towards the mirror M2. The image of mirror M2 can be seen in the mirror M1. This M2 dash is the virtual image of mirror M2. The image of this mirror M2 will be parallel to the mirror M1, but in actual these two mirrors are perpendicular to each other, mirror M1 and mirror M2, which is fixed, mirror M1 is movable. But the image of mirror M2, should be parallel to the mirror M1 to get the interference pattern. The light from the source fall upon a glass plate P1. Here light will reflected towards the mirror M2 and here it will reflected towards the mirror M1 and it will be back and then it will travel the twice path as compared to the light which is refracted towards the mirror M2. So, we cannot get the coherent source and we cannot get the two lights in a phase. So, what we require? We require the another glass plate. That glass plate is known as the compensate plate, so that this ray which is moving twice can be compensated in the reflection of the light and it also cover the two path as in case of the reflected light. From here you see that first it will go this side and then it is reflected and it is coming back if we talk about the ray which is reflected. If we talk about the ray which is refracted, it is if we are not using here the compensatory plate, then it will directly moving towards the mirror M2. But if it will directly move towards the mirror M2, we cannot get the two lights in a phase. By introducing this plate P2, we can get the phase light in a phase, and then the path of this ray 2 will be equal to the path of ray 1, and then these two rays will be in phase, and then we can get the coherent light we can observe in the telescope. This is the diagram and this is the construction of the Michelson interferometer. Its main optical path are two plane mirrors M1 and M2 and the two similar optically plane parallel glass plates P1 and P2. These are the basic requirement of the interferometer. The plane mirrors M1 and M2 are silvered on their front surfaces and are mounted vertically on two arms at right angles to each other. Their plane can be slightly titled about vertical and horizontal axes by adjusting screws as at their back. The mirror M1 is mounted on the carriage, provided with very accurate and fine screw, and can be moved in the direction of the arrows. The plate P1 and P2 are mounted exactly parallel to each other, and these are inclined at 45 degree to M1 and M2. The surface of P1 towards P2 is partially silvered. After partially reflection and transmission at O, the ray 1 travels through the glass plate P1 twice, while ray 2 does not do so even once. Thus, the absence of plate P2, the path of the ray 1 and ray 2 are not equal. The equalize these paths, a glass plate P2 having the same thickness as P1 is placed parallel to P1. P2 is called the compensating plate. From the fringes depends on the inclination of M1 and M2. Let M2 be image of M2 formed by the reflection at the semi-silvered surface of P1, so that OM2, this OM2 dash is equal to OM2, means we are having a image of this M2 in the mirror M1, and these two are equal, means the mirror M1 and the image of M2 are equal. The interference fringes may be regarded to be formed by the light reflected from the surface of M1 and M2 dash. This one. Thus, the arrangement is equivalent to an air film enclosed between the reflecting surface M1 and M2 dash. This is the condition we have defined here. When for the circular rings, when M2 is exactly perpendicular to M1, means two mirrors are perpendicular to each other, but the image of M2 should be parallel to the mirror M1. The film M1 M2 dash is of uniform thickness, and we obtained the circular fringes. In the diagram, we see that P1 and P2 are at distance of 2d, and here is the angle is theta, and we can get 2d cos theta. These are the two plates P1 and P2, these are the two mirrors, and here there are two S1 and S2 are two sources, virtual sources we are getting from the single sources. Next is, here we get the circular rings in if the two mirrors are perpendicular to each other. We will discuss about the straight fringes also. Welcome back students. Then up to now we discuss about the circular fringes in case of Michelson interferometer. We can get the different other type of fringes in the Michelson interferometer. Then we can get the straight fringes also. How we can get the straight fringes? When the mirror M2 is not perpendicular to M1. In the circular fringes we discuss about that mirror M2 is perpendicular to the M1 and image of M2 is parallel to the mirror M1, but in this case these are not parallels. It means the air film between the M1 and M2 dash is of the wedge shaped. Since the light is incident on the film at different angles, the curved fringes with convexity towards the thin edge of the wedge we will obtain. In this case here we see, in this case a wedge film is introduced between the M1 and the image of M2. If the thickness of the film is very small, the fringes are particularly straight. Means if we take the air film in between the M1 and M2 dash is very, thickness of air film is very less, we can get only the straight. The case of B we will get. The fringes corresponding to t is equal to 0 is perfectly straight. These fringes are formed near the film and are visible up to the part different completely much smaller than that in case of the circular fringes. Now, more detailed diagram of Michelson interferometer. We discuss about the formation of the fringes. Means here we are having the mirror M1 and image of M2, which is represented by the M2 dash. Means we here the source, and by these mirrors we are getting the two virtual sources which are represented by the source S1 and S2. Here these sources are parallel to each other vertically, and then source S. Here is a beam splitter and light fall upon M2, and then we can see the image in the mirror M1 here, and circular fringes we will get. It means these two mirrors should be perpendicular, M1 and M2, and the image should be parallel. Another case, here we talk about that the fringes are straight. How we can get the source should be coherent, and then it will fall, the monochromatic source we use, and to get the interference we get the coherence, and then beam splitter you use. Now see the position of the mirror M1 and M2. This M2 is slightly tilted, means it is wedge shaped. Now this mirror M1 is shifted and mirror M2 is shifted, and the image of M2 is now cut the mirror M1. And in this case the thickness T is equal, thickness of the air film is in between them is 0, and we can get the straight lines. This is the case of the monochromatic light. If we use the white light source, then here we get the colored fringes on the screen. White light source, we have the beam splitter compensating plate which is required just to get the two rays in a same phase, and then on the screen we get the straight fringes, as in case of the monochromatic light also. This here we see this is a beam splitter, and then we can get the straight fringes. Now we discuss some problems about the interference. Now first we take the first problem. In an interference pattern at point we observe the 12th order maximum for lambda 1, means wavelength is 6000 angstrom. What order will be visible here if the source is replaced by the light of wavelength lambda by 2, whose wavelength is 4800 angstrom? Then what do we use in the formula? Here just we use the double slit interference. The distance of x of the bright fringe from the center, zero order fringes, is defined as, this is the formula, x is equal to d divided by 2d n lambda, where n is equal to 0, 1, 2 and so on. Thus as a given point n lambda is constant, or we can say n1 lambda 1 is equal to n2 lambda 2. Now we have n2 is equal to From here we can calculate the N2. What we are calculating here, that what order will be visible if the source is replaced by the light of lambda 6000 angstrom to lambda 2 4800 angstrom, then N2 is equal to N1 lambda 1 by lambda 2 is equal to 12th. And what is N1? 12th order. 12th at the 12th order, the maximum wavelength is this one. At what order we can get this? Then lambda 1 by lambda 2, we put the 6000 divided by 1400. It means if the light source change, then the fringe will be change. Now we will get N2 is equal to 15. It means at the 50th order is visible if the source of the light is 4800 angstrom. Next problem. Two straight narrow parallel slits 2 millimeter apart are illuminated with a monochromatic light of wavelength 5896 angstrom, which is a sodium light. Fringes are observed at a distance of 60 centimeter from the slit. Find the width of the fringes. This is the formula to get the width of the fringes. The interference fringe width for the double slit is given by x is equal to d lambda by 2d. What is the value of 2d? The two straight narrow slit are 2d is equal to 2 mm. We can convert it into the centimeter, which is equal to 0.2 centimeter. And what is this d? D is the fringes observed at a distance of 60 centimeter from the slits, and d is equal to 60 centimeter. The distance between the light source and the screen is a 60 centimeter. The value of lambda is 5896 angstrom. Then we convert it into the centimeter. As we already convert the d into centimeter, then lambda is in the centimeter. Then we can write it as 5896 10 to the minus 8 centimeter. The fringe width, we will put all the values here, we will get is equal to 1.77 into 10 power minus 2 centimeter after solving the equation. Next, problem 3. The two coherent beam of wavelength 5000 angstrom reaching a point would individually produce intensities 1.44 and 4.00 units. If they reach there together, the intensity is 0.90 units. Calculate the lowest phase difference with which the beam reach that point. Means we are calculating the phase difference. What is the formula of phase difference here? First, the resultant intensity at a point due to two coherent waves of amplitude A1 and A2 reaching the point with the difference delta is given by, this is the formula for the to get the intensity, maximum intensity or minimum intensity I. A1 and A2 are the amplitude of the two waves. Then we can write it as I is equal to A1 square plus A2 square plus 2A1A cos delta. I is equal to I1 converted into the amplitude converted into the intensity, I directly proportional to square of the amplitude. So we write it in terms of intensity, I is equal to I1 plus I2 plus 2 root I1 I2 cos del. I1, what is the value of I1, is equal to 1.44 and I2 is equal to 4 and I is equal to 0.9. We are calculating the delta here. Then what is intensity? This I is equal to 0.9, we put here, then put the value of I1, then put the value of I2, and here I1 and I2, take the square root of that and then multiply by the 2 and this cos delta. After calculating this, cos delta is equal to minus 0.958. Now cos, as cos 180 minus theta is equal to minus cos theta. So we can get cos 180 degree minus delta is equal to 0.9458. 8. Here we can take the cos inverse and then we calculate the value of delta, which is equal to 161 degree. Means this is the lowest phase difference with which the beam will reach at a destination. Next problem, find the ratio of intensity at the center of bright fringe in an interference pattern of the intensity at a point 1/4 of the distance between the two fringes from the center. Again the same formula we will use, the resultant intensity at a point due to two coherent waves of the amplitude A1 and A2 reaching the point with the difference delta. This is the phase difference which is given by I is equal to A1 square plus A2 square plus 2 A1 A2 cos delta. If A be the amplitude of each of the two interfering waves, then the resultant intensity at any point on the screen is given by A1 is equal to A2, then we is equal to A. Then we can write intensity is equal to 2A square 1 plus cos delta, where delta is the phase difference between the two waves at that point. If we talk about the bright fringe, then delta is equal to 0, 2 pi, 4 pi and so on. So that I naught intensity at a first point at the delta is equal to 0 is equal to 2A square 1 plus 1 is equal to 4A square. The phase difference between successive fringes is 2 pi. Thus the phase difference at the point distance 1/4 of the distance between the two fringes from the center will be pi by 2. So we can write I1 is equal to 2A square 1 plus cos 90 degree. Pi by 2 is equal to 90 degree. So put the here the value of delta is equal to 90 degree and the value is equal to 2A square. We can find out the ratio between these two. I naught divided by I1 which is equal to 4A square divided by 2A square which is equal to 2. This is the ratio of the intensity at the center of bright fringes in an interference pattern to the intensity at a point 1/4 of the distance between the two fringes from the center. Next problem is based upon the Fresnel biprism arrangement. The Fresnel biprism arrangement is set with the sodium light whose wavelength is 5893 angstrom and the field of view of the eyepiece 62 fringes are observed. How many fringes shall we get in the same field of view if we replace the source by the mercury lamp using the green filter whose wavelength is 5461 angstrom? It's a very easy problem. Again we have the let I be the length of the field of view and n be the number of fringes in it. Again we use the same formula of the to find out the fringe width I by n which is equal to d lambda by 2d. Here we take the adjustment n multiply by the lambda and here we take the I this side, but this value is again is the constant. Then the same formula we use n1 lambda 1 is equal to n2 lambda 2. n1 the value is 62, lambda 1 5893 angstrom from here and lambda 2 again we have 5 here lambda 2 is 5461 and then calculate the n2. The value is 67. It means 67 fringes we get in the same field of view if we replace the source by the mercury. The next problem is interferent fringes in the biprism are formed by superposition of the two coherent light beams of wavelength 6 into 10 power minus 7 meter. If a thin plate of material having the refractive index 1.6 is replaced in the path of the one of the beam, the central fringe shift to the place previously occupied by the 10th fringe, then what will be the thickness of the plate? This formula we used and we calculate already. If the thin film of mica sheet or any sheet will introduce between the path of the two rays, then the shift of the central fringes is given by x naught is equal to d divided by 2d mu minus 1 t. This is mu is the refractive index and t is the thickness. The fringe width is equal to d lambda by 2d, so that we can get d by 2d is equal to fw by lambda, which is represented by the fringe width. Then we can get x naught is equal to fw mu minus 1 t by lambda. As we calculate the t, so we take t this side and all the terms that side, we again put the value x naught, which is equal to 10th fringe. Here we have given the 10th fringe, and lambda, the value of lambda is 6 into 10 to the power minus 7 meter. Refractive index already given, which is 1.6, mu is equal to 1.6. Put all the values in this formula and we can calculate the thickness of the mica sheet or any sheet which is introduced between the path of the ray, which is equal to 1.0 into 10 power minus 3 centimeter. Next problem on same based upon the sheet which is introduced between the path of the ray, introducing a thin sheet of mica whose thickness is 12 into 10 to the power minus 5 centimeter in the path of one of interfering beam in the biprism arrangement. The central fringe is shifted through a distance equal to the spacing between successive bright fringes. Then calculate the refractive index of mica sheet if the wavelength is equal to 6 into 10 power minus 5 centimeter. The same formula we will use to get the refractive index, where the shift x naught of the central fringe is given by x naught is equal to fringe width multiplied by mu minus 1 t divided by lambda. Mu minus 1 t, we take mu minus 1 t this side and other term this side, because we are calculating the refractive index mu. Then the value of x naught is equal to fw, fw is the fringe width, and lambda is equal to, from here we take the lambda 6 into 10 minus 5 centimeter, and thickness already given, which is 12 into 10 minus 5 centimeter. By putting all the values here, we can get the refractive index, which is equal to 1.5, which is the refractive index of the mica sheets between the path of the ray. Next, similarly based upon the, but here we calculate the wavelength of light. A thin film of mica sheet whose refractive index is equal to 1.6 of 7 microns thickness introduced in the path of one of the interfering beams in the biprism arrangement shifts the central fringes to the position normally occupied by the 7th bright fringe from the center. Now we calculate the wavelength of light used. The same formula. Now in this case, we take the lambda this side, because we are calculating the lambda, we put all the values here. X naught is equal to 7 micron thickness, so we write 7 fringe width, and mu is equal to 1.6, the refractive index of the mica sheet. Thickness is given by 7 micrometer, then 7 into 10 power minus 4 centimeter, this micron, and this is the fringe width, which is x naught 7 fringe width. Then calculate the lambda, the value lambda is 6000 angstrom. Means by using the mica sheet, by using this formula, we can calculate the wavelength, we can calculate the thickness, we can calculate the refractive index, we can calculate the fringe width also. Next is calculate the thickness of thinnest film whose refractive index is 1.4, in which interference of violet component lambda is equal to 4000 angstrom of incident light can take place by the reflection. Here we use the thickness of the thinnest film. Now the condition of the constructive interference of the light reflected from the film of thickness t is given by 2 mu t cos theta is equal to 2 n plus 1 lambda by 2, where the value of lambda is equal to 0, 1 and 2. This formula we get the transmission of light through the slab, and we already solved this formula. we can put it here the value, if the normal incident is here, the value of theta will be 0, and for the minimum thickness n should be 0. So, we can write 2 mu t is equal to m lambda, here cos theta is equal to 1 and n is equal to 0, then we can get only this part lambda by 2 from this side, and from this side we have 2 mu t. Then 2 mu t is equal to n lambda, we calculate the thickness, then take other terms this side, means t is equal to lambda by 4 mu t, then we can calculate the t is equal to 714.3 Armstrong. The another problem is a thin slab in a thin soap film whose diffractive index is 1.33 seen by the sodium light of wavelength 5893 angstrom by normal reflection appears dark. Find the minimum thickness of the film. The same formula we will use here. Here we will put the condition for the destructive interference of the light reflected from a film of thickness t. Now, we put 2 mu t cos theta is equal to n lambda, as the ray fall normally, then theta is equal to 0 and minimum thickness n should be 1. So, from here we have the value of n lambda, n is equal to 1, cos theta is equal to 1 as theta is equal to 0. So, t is equal to lambda by 2 mu, which is equal to, by putting all the values here, mu the value of mu is 1.33 and the value of sodium light lambda is equal to 5893 here, and then thickness is equal to 2215 angstrom. The next problem on the basis of Newton's ring. Related to the today's lecture, Newton's ring are observed normally in the reflected light of the wavelength 5.9 into 10 power minus 5 centimeter. The diameter of the 10th dark ring is 0.5 centimeter. Find the curvature of the lens and the thickness of the film. This is the formula. The diameter of nth dark ring. The nth dark ring formula is dn square is equal to 4n lambda r. Here dn, the value of dn is equal to 0.5 centimeter, and we are talking about the 10th dark ring. So, n, the value of n is equal to 10, and lambda wavelength, which is given by 5.9 10 minus 5 centimeter. The value of r is equal to 106 centimeter. By putting all the values here, means dn, by putting the value of dn, n and lambda, we can calculate the r. R is equal to dn square divided by 4n lambda. The value of r is equal to 106 centimeter. If in this manner we calculate the curvature of the lens, now we calculate the thickness of the film. For the thickness t, to calculate the t, the film corresponding to the ring of diameter d, then we have 2t is equal to d square by 4r. Then we put the value of r from here to in this equation. D, we have d is equal to 0.5 centimeter. By putting this value, we can also calculate the thickness of the film, which is equal to 3 into 10 minus 4 centimeter. Next problem, again based upon the Newton's ring, a convex lens of radius 350 centimeter placed on a flat plate and illuminated by monochromatic light gives the sixth bright ring of diameter 0.68 centimeter. Now, what we calculate? The wavelength of light used to get the fringes of this much radius and this much diameter. Now, here the diameter of nth bright ring is equal to dn square is equal to 2 into 2n minus 1 lambda r, where n is equal to 1, 2, 3. Then r is equal to, the radius of convex lens is equal to 350 centimeter, and we are talking about the sixth ring, then n is equal to 6 and diameter and dn is equal to 0.68 centimeter. We put all these values in the above formula and we can calculate the lambda, which is equal to 6.0 10 power minus 5 centimeter and 6000 angstrom. The next is the next problem based upon the Michelson interferometer. When the movable mirror of the Michelson interferometer is moved through 0.5896 mm, a shift of 200 fringes is observed. What is the wavelength of light used? This numerical based upon the Michelson interferometer. The distance x moved by the mirror when n fringes cross the field of view is given by x is equal to n into lambda by 2. Now, lambda is equal to 2x by n. The value of x is 0.5896 millimeter and n is equal to 200, and by putting this value in this equation we can get the wavelength of the light used to get the 2000 fringes of this much thickness. Then lambda is equal to 5896 angstrom. Thank you.
Dear friends, we hope that with today's lecture you have been able to understand the concept of light in a better terms. On that note, we would like to thank Dr. Bansal for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.
Thank you.